Yo, 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 yo. All right, we're going to talk about exponential growth. So, with exponential growth, we have a different formula. It's very similar to exponential functions, but we're just adding this 1 plus in there. And the reason why is exponential growth has a growth factor. Okay, and that's a growth factor is a rate, and we use it as a percentage. So I'll show you exactly what I'm talking about and what this means. But this is just a type of an exponential function. We're also going to talk about compound interest, which is also just another version of an exponential function using exponential growth. Okay, so here is your formula for exponential growth. Okay, and it's the same thing as an exponential function, but now this b, we're really just changing it to 1 plus whatever the rate is that we're growing by. When I simplify this, it's going to look exactly like our original exponential function. Okay, so again, we'll look at it with some examples. So here I have Hillville. It's a town, okay, population 5,000 people. So, and then it grows at an annual rate of 15%. So they're growing by 15% every single year. That's what annual means. What will the estimated population of Hillville be in 5 years? So here's their growth rate. So I can plug this into my formula. So A is still our initial value. So I have, so I have f of x is equal to my 5,000 people is where we started. Now we're growing at a rate of 15%. Well, 15% is 0.15. So we're really growing at 1.15 because that's 15% plus our initial rate of 100%. That's why we're adding the 1 to it. Okay, so we're growing at a rate of 15%. So I did 1 plus 15% is 1.15 to the power of x. Now in this situation, x represents the number of years at which we want to plug in to figure out what the new population is going to be. Okay, so x represents the number of years. So if we want to know what the population is going to be in 5 years, that's what I'm going to plug in for x, and then I just solve it. So again, it looks just like an exponential function, but now I'm taking that rate, that growth rate, and I'm adding a 1 to it, and then that's going to be my growth factor. Okay, and that's going to be what our constant ratio now is. So now this is where we need calculators. Okay, and this is where I'm going to plug in 5 for x. I'm going to do 1.15 to the power of 5 because that's for 5 years. And then afterwards I'll multiply it by 5,000 because that's my initial cost. Okay, so when I do 1.15 to the power of 5, oh, sorry, there we go. I'm working on my calculator right now. So after multiplying, I get 2.01. I rounded to the nearest hundredth. Okay, so that's 2.01. So now I'm going to multiply that by 5,000. And I'll get 10,057 by rounding. Okay. So 10,057. So that would be the new population after 5 years. So the population has doubled by growing by 15% each year. Okay. Now, population of Valleytown, also 5,000 with an annual increase of 1,000. So now we have a different town, starts at 5,000, but now every year it's increasing by 1,000. Can the expected population of Valleytown be modeled with the exponential growth function? Okay, so we start with 5,000 and then we increase by 1,000 each and every single year. Is that exponential growth? And the answer would be no. That would be a linear function because it's a constant rate of change. So I could actually write that as a linear function because that'd be 1,000x and the starting value is 5,000. So that would be 5,000 plus 1,000x is equal to y. And then now I can plug in however many years. So after 4 years or 5 years, I would plug that in, and now the population would be 10,000. And so on and so forth. Okay, so this would not be an example of exponential growth. So I'll do one more example with you, and then I want you to try this second one on your own. So if I have an initial value, if I want to write an exponential growth function for each situation, initial value of 100. So there's that first value. Increasing at a rate of 5%. So that's 1 plus 5%. Well, 5% is 0.05. So that means I'm going to have times 1.05. And that's to the power of x. So there's an exponential growth function increasing at a rate of 5%. Okay, try this one on your own. So initial value 1250, we are increasing at a rate of 25%, so that'd be 1.25, all raised to the power of x. Okay, so now what we're going to do is we're going to take this and we're going to talk about compound interest. So compound interest is a special formula that is a type of exponential growth. Here is my formula for compound interest. Okay, so put a star next to it and make sure we know what each piece of the formula means. So what we're doing is we're taking that rate and we are now adding an extra piece to it in our formula, because it depends on how many times it is compounded. So we'll talk about what that means. So compound interest is when hopefully we understand what interest is, because we talked about that with simple interest before in 7th grade. Okay, compound interest is when, we'll go back to our definition and our key terms. Compound interest is when the interest that we earn is paid both on the initial principal that we pay, that we start off with, but also on the interest that's already been earned as well. So you're actually earning interest on the money that you've earned. So it's one of those things where compound interest is considered to be one of the most powerful things in the world, because if we earn compound interest, it starts to grow exponentially, and it can grow very, 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 very fast. Okay. So here's our formula. We'll talk about how to use this formula within this example. So here I have a deposit of $3,000. So there's my initial amount. A deposit's that initial amount. The interest is 8%. Okay, so there's my interest rate. There's the growth rate of 8%. But it is compounded quarterly. So what quarterly means is that it is compound 4 times every single year. That's where this n comes into play. Okay, so that means it's compounded 4 times every single year. So that means every single 4 times a year, it is resetting and earning interest again. It is resetting the amount that it's earning interest on, which is a good thing. That means the more we compound, the more money you actually end up making. So we're going to use our formula to figure out the value of this initial deposit at the end of 5 years. So amount deposited was $3,000. There's my principal. That's my initial amount. That's my starting point. So we have 3,000. Now that's times 1 plus whatever the rate is. Well, the rate was 8%, so that's 0.08. And that's divided by how many times we are compounding it. Well, we're compounding it 4 times. So that's 0.08 divided by 4. Because quarterly means 4 times. And that's all the power of time in years times how many times we're compounding it. Well, that was, again, 4 quarterly times 5. So it's going to compound it 20 times. That's 4 times every single year. Here's my formula. So this is where, again, we'll use a calculator to do that 0.08 divided by 4, which is 0.02. So I have 3,000 times 1 plus 0.02 compounded 20 times. So again, it's an exponential growth function. And then there's my value that I'm going to multiply within my calculator. I'm going to do 1.02 to the 20th power. And then I'm going to multiply that by 3,000. So after multiplying, I just did the work on my calculator. After multiplying, we get 4,457.84. So the new amount in this account the value of this account now after 5 years is $4,457.84, and that's without adding any money to it. They just did a deposit, and then it was earning compound interest. After 5 years, they've made $1,457.84 by letting it sit there and do nothing. Okay. Now, for part B, it's asking, will the value of this be greater after 15 years if it is compounded annually rather than quarterly? So 15 years if it's compounded annually rather than quarterly. So what I want to do here is annually means it's just compounded once a year. It's not compounded 4 times a year like quarterly. So what I want to do is I need to use 15 years into my formula. So we're going to start again with our initial amount. That's 1 plus that 8%, and that's once a year, right? But now it's just times 15 times once a year. Okay, so now this is my new value that I'm trying to figure out. Okay, so then I can simplify this. Annually means once a year, so that's just going to be 1.08 15 times. Okay, and now I can figure out the amount in the account, and I'm going to plug that into my calculator. Now, before I plug this into my calculator, though, I'm also comparing this with what happens after 15 years quarterly. So that's going to be the same formula we had before, because that's quarterly compounded, but that's going to be 15 times 4. So what I'm comparing is what's the account going to be worth with these two exponential growth values. So same rate, same initial amount, same amount of time, but this one was compounded 4 times a year, this one was compounded once a year. And I want to see what's the difference in the accounts. So I'm going to plug these values into the calculator and then solve. Well, if it was compounded annually, it's going to be worth $9,516.51. That's pretty good. 15 years, we went from 3,000 to 9,000, so it's tripled in value. More than tripled in value. For doing nothing, didn't add any money. Okay. If we compounded it quarterly, it'd be worth 9,800. Whoa, that was weird. $843.09. So by compounding it quarterly, this account, we made an extra $300. Okay, so compounding it quarterly would make it worth a little bit more. Okay, compound interest. There's a few examples. It's just another type of exponential growth. I want you to try this problem on your own. So use your compound interest formula and see if we can figure this one out. So try it, pause it, see how you do. If you get it wrong, no big deal. Okay, so account is open with a deposit of $5,000. So there's your initial amount. That's your principal. Now I know it's 1 plus whatever the rate is. The rate's 6%. That's 0.06. Compounded monthly. So monthly is the number of times it's going to be compounded in a year. So that's 12 times a year. Okay. So then that's going to be after 12 years. So 12 years times however many times it's compounded, which is monthly. That's 12 times 12. Okay. So I want to know the total value in the account after 12 years. So here's my formula. This is the work that I need to do. So when I work this out, I'll get 5,000 times 1 plus 0.06 divided by 12. Well, that's 0.005. And we know this is 144. So my work is 5,000 times 1.005, all to the power of 144. And this is where I can work it out in my calculator, figure out what 1.005 to the 144th power is. So let me just plug that in real quick. All right, I get 2.05, and then it goes 0.7, and it keeps going. And I got to multiply that by 5,000. Well, the account has then doubled in 12 years, and it's now $10,200 $1,253.75. Okay. That's all I got for you guys. So things to remember. And we're going to focus on compound interest. Quarterly means 4 times. Monthly means 12 times. It might go biannually. So biannually means twice a year. So it's every 6 months. Okay? All right. I want you to write an exponential growth function for this situation. And then actually I want you to add to this too. So here's your initial function I want you to write, but then find the value after 5 years. Let's go 6 years. So I want 2 pieces to this one. All right, that's all I got for you guys. Thanks for watching. If you guys have any questions, let me know, and then we'll get some extra practice on this. Gordias out.